Vanakkam. Welcome to this course on biomedical instrumentation. So far we have been looking at electrode theory and we have looked at microelectrodes in the previous set of videos. In this video we will look at some practical hints in using electrodes and some recording problems that can happen in measurement with two electrodes. Some of the practical hints. One critical approach is to use similar materials or the same metal, that the electrode and the exposed lead wire must be of the same material. Why? Because otherwise there will be some electrochemical reaction that could happen and corrosion and increased noise could happen. Avoid using solder unless it is insulated from the electrolyte. It is absolutely important. So, do not use solder to connect two metals. Soldering is not permitted in this method. Avoid using solder. So, essentially in your fabrication we need to use welding or crimping the lead wire to the electrode for a secure bond rather than using solder to connect two points of the electrode. Although they are made of the same metal, solder should not be used in the middle because this will cause two dissimilar junctions, one with the first metal and the other with the second part of the same metal. And you need to use electrodes of the same material to ensure that the half cell potentials are comparable or similar, and so that the DC offset at the amplifier input is minimal. Right. This reduces noise and prevents saturation in high gain amplifiers, because if the amplifier is going to have a very high gain, if the DC offset is very high, then the amplifier will go to saturation very quickly. The basics of electronics. Yes. And the other is a mechanical problem. You want to make sure that the electrodes do not come off from that. You have to make sure that there is proper adherence. You use an adhesive and it loses, if the adhesive tack loses effectiveness. The solution is to use highly flexible and strong lead wires, and then you use these lead wires, you tape them to the skin with sufficient slack to minimize torsion or bending on the electrode. The other is avoiding lead wire failure. This happens often because of a mechanical failure, right? Often what happens is when it enters or touches the electrode, that is where the failure happens. You have to provide strain relief, right? So, you need to have a tapered insulation region so that sufficient mechanical strength is providing, and distribute flexing forces over a relatively large area or the large bending diameter to ensure that it is not bent critically at that point so that it breaks. That is a mechanical strength problem. And then there are challenges with insulation materials. For example, polymeric insulation sometimes absorbs moisture, right? Then what happens is this increases conductivity, and then there might be some triboelectric artifacts from bending insulation. Right? So, we need to test for flexibility in variable electrodes and use thick insulation layers in implantable electrodes to ensure the corrosion does not happen. The other is the effect of high frequency currents. Suppose you use high frequency currents like in an electrosurgical unit, right? In an electrocauterizer type electrosurgical unit. Sometimes the currents can be of the order of 500 kilohertz. This can cause rectification in the electrode because of large low frequency DC voltage shifts. So, this also another thing is that sometimes ECG interference from other measurements cannot be filtered, and we need to make sure that the recording is done using high fidelity equipment. What is high fidelity equipment? The input impedance of the amplifier must be higher than the electrode source impedance, must be not just slightly higher, must be orders of magnitude higher. Otherwise what will happen? Otherwise there will be loading that will happen, is it not? Voltage divider, in a voltage divider loading will happen, otherwise current will flow through the amplifier, which is not a desirable situation, right? This low impedance, if there is low input impedance, this essentially reduces the signal amplitude, and comparably noise amplitude will be higher, and essentially reduces signal to noise ratio, is it not? Significant waveform distortion happens. For example, this effect has been demonstrated by Geddes and Becker in 1989 in ECG recordings. if you have low input impedance, what happens? For example, here is a measurement that I am having, that I am doing with 2 electrodes, right. Here are 2 electrodes with 2, this is R2 C2, right, or R3 C2, whatever, right, and I am having 2 electrodes. I am in a bipolar configuration. I am measuring with say EMG, for example, right. In this case, if I am measuring from the surface biopotential, say surface EMG, you are essentially interested in measuring small potential differences, right. In this case, noise will play a critical role. The output voltage of, essentially you are trying to amplify this difference in a differential amplifier, amplify this in a differential amplifier configuration. The output voltage of this amplifier that is used to measure this bioelectric events is not always accurate representation of the fundamental phenomenon, because this is the desired voltage difference, right. This is the desired voltage difference, and then some other unwanted voltages are also there. The desired voltage is the signal, and all the unwanted voltages are the noise. It is necessary for you to use electrodes that are in 2 electrode configuration, electrodes that are similar and comparable, so that the half cell potentials are common between the two, right. It should not be that one electrode is made of one metal or material and another is made of another material. So, you need to use similar metals or materials for this purpose, right. So, and there is electrolyte noise. So, essentially the stability of the potential of an electrode, in this case an electrode of an electrode, essentially depends on the material that you use and the how you fabricated that electrode. This material is mostly used for low noise recordings, right. In silver, for example, recording electrodes means silver chloride electrodes. For example, a silver chloride electrode as a relatively stable electrode. And then there is the electrolyte skin noise. There is electrolyte noise, and then there is electrolyte skin noise. Now, if you are interested in what is happening under the skin, then you need to minimize the noise that is produced due to the skin, because it is a difficult task. For example, EMG signals and other noise sources will always, there will always be contamination. You can increase the diameter of the electrode, that reduces noise, but then that also reduces the spatial resolution. Then there is movement artifact. When there is movement due to movement of the patient, when there is movement due to stretching of the skin or movement of the skin, this essentially creates potentials that are sometimes higher than the measured potentials of interest and have similar frequency characteristics. How do you remove them? Normally, when the patient is relaxed and if you use high quality electrodes, then the recording is not distorted by movement artifact, but then you cannot assure that this is the case when you are making. So, artifacts sometimes in the skin electrode can be of the order of several hundreds of microvolts, close to millivolts. When the electrode is moved parallel to the skin, then this happens quite often. When the electrode is moved perpendicular to the skin, then the voltages can be as high as 1 millivolt, right. Then there is electrolyte noise that is caused due to cable movement. One is the electrode movement, the other is the cable movement. Cable movement causes an artifact in, for example, in an MRI scanner, a strong magnetic field of an MRI scanner. It can be avoided by amplifying the signal before it enters the cable, so that noise is minimized, artifact is minimized. And then thermal noise. All cables will have resistance, and all resistances will produce a certain amount of thermal noise, and that is related to this as 4 times square root of 4 times kTBR, where K is the Boltzmann's constant, which is 1.38 into 10 power minus 23 joules per Kelvin, and T is the temperature in Kelvin, B is the bandwidth of interest, and R is the resistance in ohms, right. And we can find out the RMS thermal noise using this formula. Now, let us say that I am designing a neural probe with metal electrodes, metal microelectrodes. The resistance is, it says 2 ohms, it is actually not 2 ohms, it is 2 mega ohms. You must design a head stage amplifier that has an input impedance that is greater than 20 times the electrode impedance, and the electrode impedance is 2 mega ohms. Thermal noise power bandwidth is 5 kilohertz, and the temperature is 37 degree Celsius. So, that is equal to 310 Kelvin. So, I am interested in finding out VTH, what is the thermal noise, that is going to be the square root of 4 KTBR. What is K? That is square root of 4 into K, we saw from the is 1.38 into 10 power minus 23, 1.38 into 10 power minus 23 into T is 310, B is bandwidth, which is 5 into 10 power 3, 5 kilohertz, R is 2 into 10 power 6 in ohms, square root of this. Compute this using a scientific calculator. If you compute this, you will find out that this is actually about 13.1 microvolts. Check this computation and let me know if this is wrong. Consider that neural recordings are of the order of hundreds of microvolts. 13.1 microvolt is actually a significant amount of thermal noise. So, you need to design the amplifier such that this noise becomes insignificant with respect to the signal. This is signal. So, you need to amplify the signal so that this noise is becoming much smaller in comparison, right. So, with this we come to the end of this video. In this video, we looked at some practical hints in using electrodes, and we looked at some recording problems and measurement with while using 2 electrodes, and we also looked at a numerical problem.